let's see. So Vaishnavi, when you say localization, so I mean, this is going to be a topic which is going to be very important, of course, localization. So after we discuss, I will tell you some references, and then we can see. You should read about it and then tell me later. But first, maybe since Vaishnavi has already studied some of localization, maybe you can tell us uh, what is it that you understand.
Okay, like I was studying from integral domain. In the books which I had studied, they introduced the field of fractions. They constructed the field of fraction from there,
Okay.
and yeah.
Okay, that's one. Okay, and anything
Yeah.
else?
Then in the integral domain, they took a particular set, that multiplicative set, and they constructed the inverses and uh, inverses, like localization of like we can call integral domain to be D, and they constructed the M inverse. Uh, yeah.
Okay,
Uh,
right. So M is kind of sitting inside this,
yes,
and
yes, yes. And it is a multiplicative set, and
then you construct. So this is a slight generalization of this,
yeah.
right? So
Yeah.
this is what you have done, and then after this, anything more?
No, no, that's all I have read. Like,
Okay, okay, right. Okay. So then let's do one thing. Let me say this thing for commutative rings. Okay. And
yeah,
then you can always, like Aryan, for example, you can always think of Z and Q, and that's actually a very important example of localization. But also maybe a small
Yes,
other example
yes,
we
sir.
will do. Yeah, that's one thing. One of the another example we will do is maybe Z localized at some prime. That's where things get interesting. Okay, so those two examples maybe, and there are plenty, but let's see. Localization can be done without commutative rings. One doesn't even need commutative rings. So like Vaishnavi, so far you have done done in integral domains. One doesn't need
yeah.
integral domain.
Next it was like they introduced unitary ring, and they said that localization is a special case, and I did not read that part. Like I
Ah,
was looking into,
okay. So
like
can
I
you
have
tell
to.
me which book is this?
It's algebra in action. Sharia something. Algebra in actions. I
Okay, algebra in action.
Yeah.
Okay, that's okay. I seem to have heard the name, but not studied. Okay, okay. Anyways, yeah, right. So let R be a ring then. Let R a unitary ring. Yeah. So I will say a few things, and later on, Vaishnavi, if you find something which are different in that book, you can tell us next time. Okay, when you study that, because this over ring concept I is not very, I not, it's quite new to me. Okay, yeah. Yeah, I know it's a generalization of something, but again, all this will just become words. Let me get to the concept, and you should tell me next time if there are some other things which are in that book. Okay. So let R be a unitary ring. Okay. So we have plenty of examples of this. Okay. And again, S be a multiplicative set. So what do we want to do? We want to go to a bigger ring, and yeah, not, it's not necessarily bigger, but we want to go to a ring where these elements have inverses. Okay, putting Z in Q, then if you go from Z to Q, then you've gone to a ring where the integers apart from 0 have inverses, and you have completely put this ring inside that ring, meaning that this is a ring homomorphism and all the nice things,
Yeah.
all the nice things. So even with the precise definition of ring homomorphism, but you can look at it, but you understand what is kind of going on. Okay, but S be a multiplicative set. Now, why we want it to be a multiplicative set? that you will realize. But again, I should define what is a multiplicative set. So multiplicative set is just that if S1 and S2 is in S, then that implies S1, S2 is also in S, as you can understand.
Yeah, one
And
should be there.
one
Other two,
should,
yeah.
yeah, one.
Zero,
Okay, zero should not be there.
yes.
Okay, right. So let's put these things in the definition, and I mean I don't know if removing them can still make the theory work, but yeah, let's keep them. Yeah. I mean, if you keep zero in this, then then also it will work, but it will just become trivial. So let me at least remove this condition, because I can see it that it's not a problem. It just adds some trivial possibilities, but it doesn't break the theory down. I mean, it cannot, because no, I mean it can, but it doesn't, because things will still work. So now we want to, yeah, so as I said, that you want to go to a ring where you have these kind of things. You want to make sense of these elements. The idea is to make sense of these elements. Okay, and what we will be doing here is something which always happens in algebra when you're doing any kind of construction. Like yesterday we did some tensor products, and for example, anywhere. So yeah, if you do any basic ring theory, for example, the polynomial ring is there. You can, polynomial ring is doesn't really come as yeah. Anyways, let's just do it. Like, I mean, at least you know that when you define the rationals, you know how you do. You take pairs of integers and you define an equivalence relation. That's what we're going to do. Yeah. So we look at, so since I'm not assuming commutative at the moment, we'll see if that is entertaining. I mean, let's see. So if we look at R cross S, okay, and then we want to put an equivalence relation. Okay, so what should that equivalence relation be? Means, is there
Yeah,
something which you can guess?
yeah.
Yes. So what should that be?
It's R1 S2 equal to S1 R2.
Right. So that's almost what I'm going to write. So this is equal to, but because it's not an integral domain, you will realize that it's necessary. But I'll put it and not say why. Okay? But you will if you think about it, you will realize why I'm writing like this, or maybe I'm writing it wrong, because I'm not assuming commutative, so I have to, I suppose, be a bit careful, right? Okay. So sorry, I have a bit of cold. Uh, okay. So this is the condition, and you can see that this is what you would want, right? So for example, if you have 2 by 4, if you have 4 comma 2, right? Is that correct? 4 comma 2 or 8 comma 4. You know that you would want to call them the same, and this condition enforces that. Obviously, this condition, like this is same as this in this case. This is same as this in Z case or in integral domain case. But in general, this could be a nuance. It could be a different thing. Okay? But we put that condition, and you will see that it's there, sort of needed. Because because you want to invert the elements of S, right? So
Yeah,
yeah, so you want to say that S is invertible. So in the ring S inverse R, this should mean this. In the ring S inverse R, not in R, right? Because you should be able to invert out the S, right? But but then we do put it because that will force that S, that S inverse really behaves more like S inverse. I think that's more confusing, so I will just we'll see this and see. Yeah. Now the point is to see that this is an equivalence relation or not. Right? That is most important, right? We need to check that this is an equivalence relation. So is this an equivalence relation? Okay. Because first we check that it's an equivalence relation, and then we check that you can put a ring structure on the equivalence classes, and that's your ring Q if you start with Z. Okay.
Yeah.
If you start with Z, and then if you ask me what should be S, then you know it should be Z minus 0. S then
Yes,
in
yes.
that case should be Z minus 0, right? So these are the things, and one of the reasons why I've also removed the 0 is kind of now you can connect back why I've removed the 0, because this is not an integral domain. 0 could end up being there in S that will trivialize things, but it's possible. Sometimes we need to detect that triviality also for some problems. Anyways, so this is is this an equivalence relation? So what should we not check? And symmetric and reflexive are already there, written here, but we should just check transitive. Okay, so let's see if it is transitive. So assume this, and okay. So we are not just learning, if you would call it, not just looking at localization, but we are also learning how algebra works. This is something that just keeps repeating these kind of things, like what you want to do. If you clearly understand that, then you would just know how to do the construction. That's the point. Algebra, large parts of algebra is just bookkeeping, thick books. In algebra, if you realize what is going on, if you can understand it, you can do most of the things from very small number of principles. And that is very, very that's it, true independence. You're not chained down to the book, and you don't have to know every line, every theorem. You don't have to. Okay. But of course, but one has to still walk the path, I suppose. It's different for different people, but one has to still, of course, go through the work, which later on looks like very easy. But one should, but it is just maybe kind of a faith or something that algebra starts making a lot of sense. A lot of the algebra starts to look very simple. But of course, then one has to do some non-trivial algebra to do anything new. So, anyways, so this is like this. Yeah. So, what does it mean, right? It means that R1 S2 minus S1 times S is equal to 0, and right, and R2 S3 minus. So there is a S which works, right? So we can take the same S for both, because you can just multiply them, right, and take the same S. But is it any good? Now, how do you show that? We need to show how do we do that?
Okay, like we can multiply first equation by S3 and
Okay,
S2
S3.
and S1. We can multiply this by S1.
Second
And if
equation by
we add,
S1.
yeah,
Okay, but
yeah,
yeah, okay. Then you are saying we should add the equations.
yeah, yes, yes.
Okay. Okay. So we get S S3. Yes. So here we are assuming commutativity. Assuming that it is commutative, we are proceeding, and then things are just correct. Let's see, is it correct? This, and then what happens? R1, yeah, so you can rewrite this as R1 S3. But R3 S1, SS1. But now this is not correct, right? We had to adjust a few more things, I suppose. Yeah, but you can make it work, right? You should have also multiplied this side, right? We should have also multiplied this side by S2, correct? And this one by some S1, S1 extra S1, right? Then it would work. Is that?
Yes, yes,
Yeah, then
yeah.
it's just a matter of multiplying it by enough things to make it. But you'll finally end up in somewhere in S because it's multiplicative. So you'll always remain in S, and it works. It's an equivalence relation. But the question is, at but how do you make all this work in non-commutative setup? Because this is nothing. This is just what the only thing you can do. These are just symbols. Right? There's no further conditions much. So whatever you can do will be just in that range. So let us rethink this and think about how to handle this without commutativity, right? So that's fine, right? That if you have that, then you have that R cross S. We have quotiented R cross S by an equivalence relation. Then you have the equivalence classes, and then you can easily guess how to add the equivalence classes. So that's all right. You can put a ring structure. But
Yeah.
yeah, but what do you do when it is not transitive? Sorry, not commutative. That is the actual question. So just to ease things a little bit, let's assume that it's a integral domain, but let's take away the commutativity, but assume that it's an integral domain. Then this definition of the equivalence relation becomes the classical one. It is R2S1, of course, correct? It becomes a classical one, and let's see what can we do. You see, point is that one should not assume that it can be done. It might not be transitive. Okay, so one has to also keep that in the. Okay, it's not true that something you can do for commutative ring you can always do for non-commutative. What are we trying to do? We are trying to get a ring where this S becomes invertible. Okay, that can be said rigorously that you want a ring homomorphism from R to a ring where the image of S is invertible. Okay, but that I'm saying it's the same thing. once you people get more and more comfortable with this, then we can start using that language. But at the moment, so the goal is clear, right? That we are looking at a domain. So now we're looking at a domain, but not necessarily commutative. Okay, not commutative. In fact, but commutative we already did for rings in general. Just 1 minute before moving on, you can see this is quite a powerful construction in some. It's easy, but it's quite powerful. It's quite general at least, right? Because the SU can just vary, right? So it's up to you what you want to invert. And this theory tells you that you can always go to that ring where you can invert away those things. Because look, in ring, what is interesting? If you're doing ring theory, then what is interesting? In ring theory, the interesting elements are those which are not invertible. Correct? If the things which are invertible, those that lies in field theory. And that's easy. I mean, the questions that you ask in ring theory are trivial for those kind of elements, right? So the question becomes all about the things which are not invertible. The worst of the things are nilpotent, nilpotent elements. I mean, worst in some sense, but obviously they probably give you the most interesting questions. So, I mean, one has to understand the spectrum of the types of elements that are there in a ring, and yeah. But anyways, let's also. So that's what I'm saying. That this gives you the power that S is can be varied. Okay. This one, and then you have R2S3 and R3S1, right? Then or okay, fine. Yeah, what we want to show is certainly not correct. How does it work in usual integral domains?
Uh, Here it is visible. Here we can just multiply by S3 and S1, and we will be getting R2, R1 S2 minus R1 S2 S3 minus
Uh-huh.
uh, R.
R2 S1 S3, okay, and here S2.
Yeah.
Okay.
Sorry. Here it's S1.
S1. Okay, right. So you're multiplying both sides by S1.
Yes. Yes.
Okay, there is already an S1, but okay, I suppose that's what you have to do. Okay, and then what happens? Then this thing that you add them and this cancels out.
But
No.
no. No. No. No. No.
So what is the construction that you do?
Yes.
Okay, I think I've written something wrong. That's the source of the problem,
Yeah,
right?
yeah, yeah. Here we can take some
Yeah, it should have
S3
been S2.
outside.
Huh. Okay, where do you take S3 outside? Yeah, this is fine. This works. This is done, right? Yeah. Like if, as you
Yes,
said,
yes, yes,
yeah, just add it and then you are done. Right?
yes, yes, yes.
And this
Yes.
also, as often happens when you work things out, even the easy things, if you work it out, you learn more things, because now you understand. Now you can kind of feel that if you're in a non-integral domain situation, you should have this definition. You can feel that more and more
Yeah.
by looking at this, because and then you cancel out the S2, but you cannot do that in a and with it's not integral
Yes.
domain,
Yes.
and so right.
Yeah.
Okay. So it certainly works, but then again, if it's not commutative, then yeah, so then maybe it's not to erase that. There's no. Okay, then let me see. I have a master plan. I mean, if it works, yeah, maybe the in the definition we should continue to have the S. Okay. Yeah, maybe this kind of thing is. No, I think this kind of construction is purely commutative. I mean, this approach doesn't seem to work very well in non-commutative setup. So, well, now I will try to put a different kind of view to the same thing. That what you want to do is you want to look at this, right? And means this how it is in but this is imagination kind of. It's not rigorous. We have this, okay, and then you want to be able to write this. You want to exchange this, right? You want to exchange this. In the commutative world, you can just do it for free. Here, you cannot do it for free, but you can. I mean, if this thing can be written as some R3 R3 S3 inverse, then also it is fine. If okay, if S1 inverse R2 is equal to S3 this, correct? And of course, this does not make sense in R. So if you want to write this condition, erasing this, if you want to write this condition in R, then you better write not like this, but like this. It's the same. It's enough for us. We instead write this, right? So we're now looking at localization from a more down to earth perspective, because we got confused. I got confused. So we want to be able to write this product, this multiplication, right? Because you see, I mean, the point is that, yeah, there are many points here that we are not even able to prove that it is an equivalence relation. Just a minute. I mean, is it easy to show that this is an equivalence relation? Getting stuck at something. Let us see. Let us see. Let's once. Yeah, so if R is to S minus. Yeah, because either it is an equivalence relation or.
You are assuming non-commutativity, or it's a.
Non-commutativity. With commutativity is already done, na? That everything works,
Yeah, yeah, yeah.
right? Yeah, commutativity is it is a ring and everything is fine. And if and the reference for that would be, you look at Atiyah MacDonald chapter 3. where all the details are there and other very important things are there for the commutative world. But a McDonald commutative rings or commutative algebra, I think. Chapter 3, localization of rings. So this you should read. I mean, both of you should read this. Just check it out and read as much as you can. This is very, we have discussed things, so I suppose that can help you in the reading process. But non RTM McDonald doesn't look at non-commutative rings. So let us see. I want to somehow cancel this thing with this thing, right? And that is if that has to be possible, if that has to be possible, then no, but that is not enough. It's not just enough to cancel these things. Yeah, you will get a set of equations, right? I mean, if you really put it down, you will get some equations, but I don't know if that can be satisfied, right? Yeah, I'll just come in a minute. Yeah, yeah. So I mean, I think that one has to take an alternative approach. Okay, I think this method is maybe not so because you will get some equations and it's not so friendly with non-commutative thing. But yeah, but one thing that I want to say before maybe we'll stop for today is that you can write this thing. If you can write this thing like this, if your ring R is such and the S is such that you can do this kind of thing, okay, then you have more hope that you can sensibly construct a ring where S can be inverted. Is that something which is sounds okay? I don't know.
No, can you repeat it?
Right, I'm saying that if your S and R are chosen in such a way that for every S1 and R3, yeah, there is a R2 and S3 such that this happens. Okay, this can be written as that, and this can be written in a more abstract way, but if this can be done, then you see, then you at least have a sensible way to multiply your fractions. With S again in the denominator and this is again in the numerator is again something in R. More importantly, denominator is something which is again in S.
Yeah.
Very roughly speaking, right? Then you have a hope. I mean, it's not yet concretely constructed. Then you have a hope that you can construct a ring where S is invertible. Okay, that's thing. Okay, then but how to do the construction? This is what is called the OR condition. This is called the OR condition, and I suppose as it's visible, it can be written like uh, mean, yeah, maybe S and S prime or something. It can be written. So let me not get into it. It can be written in a way, but it's the same thing. That yeah, that is R3 and S3 is free. The R3 and S3 is free, right? And the R1 and this S1, S and R is given to you. So it's something like R S R uh, intersection with uh, uh, R2S is non-empty. This is what this is saying if you think about it. Okay, right? So then there is a hope. But then the point is that, so I just stop saying this is that for this to manifest, one has to take an alternate approach. And the alternate approach has to go by quotients of rings. Quotients, we have to interpret localization in terms of quotients. So what one has to do is attach this free polynomial ring. Now there was a free in free modules in tensor products. Now we will look at something free algebra. So this is a commutative polynomial ring, or maybe we have to look at this. We'll talk about it, and then you have to quotient by what you are quotienting by, and that has to be the localized ring. One has to see that that's the same construction as what Atiyah McDonald does in commutative world. So it's equivalent on the commutative world, but in the non-commutative world, it really makes it still works with this condition, which is the minimal requirement, of course. Okay, but all that needs work. All that needs work. But this theory of localization is huge. I mean, or condition and localization on commutative rings is huge, and then it goes a very long way. Localization of categories and there are many things. But maybe we'll talk about it next time. Meanwhile, you read Atiyah McDonald. That's the most important thing. Okay, that's it. So I'll stop. Okay, yeah. Thank you. I'll let you know about the next class. Mostly Tuesday as our scheduled time, I think. But yeah, okay.